Understand process variability and compare it to the specification could be a life or death challenge. If you don't believe me, just watch this video. Pretty impressive, right? Now, the question is how we can do the comparison between variability and the spec. I'm Fernando Rodriguez, and in this video we are going to review the right tool to do this comparison, and this is the capability analysis. We are going to break this learning process in 4 steps. First, we are going to review the idea, then go through the requirements for this comparison, review the formulas, and do some practice. So let's start. The idea. Imagine that you are flying a plane. You are not always stable. You have some sort of variation. And there is a spec well defined the track. So if I'm not able to fit with my variation inside the track, I'm gonna face trouble. Let's do this comparison. Pilot A versus pilot B. If you were able to see the landing points of each pilot, and you have the opportunity to choose which pilot you're gonna travel with, who will you select? Of course, the pilot A. Why? Because this guy has less variation, and as much as we can reduce variation, we are going to have a more reliable process. So we need to reduce the variation as much as possible to be able to absorb any other changes that the process may face. If we record all these landing points and we pull or move to the right, we are going to see that this is becoming kind of an histogram, showing us what values are more frequent than others. So you start observing that this has some sort of shape, okay? We can calculate the mean or the average, that is the middle point or middle value. Second step is to calculate standard deviation. Standard deviation is a measurement of variation. And standard deviation, if it's bigger, you have higher variability. With these 2 parameters, mean or average and standard deviation, we are going to be able to see or to calculate the probability of occurrence of our values. So if we have a mean or an average and I step up 1 standard deviation and step down 1 standard deviation, I'm going to have 68% of the data. If I move 3 standard deviation to each side, up and down, I'm going to have almost 100% of the data. And that is important because I know where my landing points in this example are going to be. Remember this guy? If we throw him through the ramp multiple times, we are going to have a frequency. Of course, the size of the pool is going to be the upper spec and the lower spec limit. So let's go to the point number 2, the requirements. Requirements are 2. Before we start the capability analysis, we need to review process stability and normal distribution. How we do the verification of process stability? Well, pretty easy. We make a chart that we can do in Minitab or in Excel, and we verify that the values are stable. Stable doesn't mean that we have high or low variation. Stable means that we have uniform variation, as we see here. Second requirement, how to verify normality. Normality is a little bit harder to calculate, so we are going to use Minitab. Minitab is a software for statistics. So we go through the basic statistic, the basic statistic menu, and then the normality test. In the normality test, we are going to select the column where we have the data, and we are going to have these results. You can observe that the data points are going to be close to the red line. And if you observe some funny shapes, like in the chart that we have here, is going to be not normal. But at the end, in the upper right corner, we are going to see these values. For the normal example, we have 0.905, and for the non-normal, we have 0.007. The rule is if the p-value is above 0.05, we are going to have a normal process. In the capability analysis, we are assuming normal distribution because normal distribution has symmetry and has this probability of occurrence of plus minus 1 sigma, plus minus 2 sigma, 3 sigma that we reviewed previously. If we have a skewed distribution or a non-normal distribution, we are not going to have the symmetry, and therefore we cannot run the calculations. One very common problem that we are going to face when we see the data is the bimodal distribution. When we can suspect that we have a non-normal distribution, when you have these two mountains, the shape of the histogram is like two mountains together. So if you observe this, most likely you are mixing parts. It's very common, like in the molding industry, that you have different cavities, that you are going to face this problem. Also, when you are mixing two different machines or two different lots, and these lots are having different characteristics, different distributions, and therefore you are seeing this bimodal distribution. It's very easy to break. You just investigate what is the difference, and you need to make a CPK analysis or capability analysis separate for each. If you don't have a normal distribution, you need to do a transformation of the data. There is a solution, don't worry. You can see the video that we have for transformation of data. Okay, so far we reviewed the two requirements for capability analysis that are going to be process stability and normal distribution. Number 3, the formulas. Okay, let's the show and the fun start now. Key points that we are going to review. First, we need to understand what is the short and long-term variation. We are going to review the formulas for CPK and CP and the acceptance criteria. First, we are going to talk a little bit of the indicators. We have the CPs and CPKs that use the short-term variation, and we have the PP and the PPK that are the long-term variation. What is the short-term and the long-term variation? Well, most of the time we collect the data in a short period or relative a short period of time. Okay, when we have more variation, like worn out of our tool, we have changeovers, different lot of materials, different shifts, etc. We are gonna face that this variation, or we are gonna see that this variation increase. Okay, this increased variation is gonna be the long-term variation. Let's go to the formulas. What is CP, or potential capability? Well, it's the comparison between the spec and the total variation. Of course, that the spec needs to be higher than the variation. Something that is important to say here is your variation could be outside of your spec and you can still have a good number of CP. In the example of the plane, you are flying and you know your variation and you know the size of the track in the handcraft carrier. So even if you don't see the handcraft carrier yet, you know if you fit with your variation inside the spec. So that is why it's called potential capability. And then we need to calculate the CPK, that is comparing your variation to the closest limit. Could be the lower or could be the upper spec limit. For that calculation, you are going to take the distance between the mean and the spec limit and divide into the just taking half of the variation. Okay, that is the way that we do, and we calculate that for the upper control limit, we calculate that to the lower control limit, and then we select the one that is the minimum. Why? Because the probability of making an error or making an out of a spec product is going to be related to the closest spec limit, not to the one that is far away. That's why we select the minimum value from the upper and the lower spec limit calculation. So, acceptance criteria. The minimum required to accept a CPK of a new process or a current process that we are evaluating is going to be 1.33 minimum. If we are following a critical process, we are going to require 1.67. That is for our critical characteristics. If you achieve 2.0, you are going to see a Six Sigma process. Okay, so what we learned in the section 3, the formulas. We review the short-term, long-term variation. We review what means the potential, capability, and the CPK. We review the formulas for both of these criteria and the acceptance criteria. So let's go to the point number 4, the practice. In the practice, remember, we need to verify process stability, verify that the distribution of data is a normal distribution. We need to run the analysis and report out the conclusion. So let's start with an example of a race.
También, ¿no? Hay que ver en segunda velocidad, ya las sentencias ahí, la cuadriculada que se va a preparar, no quiere que se haga humo, la victoria, Nicolás Alfonso, que va...
And we are now going to review the piston ring example, where we have 25 samples and we have a spec of 74 millimeters plus minus 0.05. So first, remember, we need to verify process stability. We need to go to the graph menu of our Minitab that is in the top right next to the stat menu. So we select the graph menu and go down to the time series plot. Select the diameter column and we are going to see this. So with this I can see that it's stable, there is no curvature, there is no one section down, one section up, there is no funny data pattern here. Okay, so let's go for the step number 2, verify normal distribution. Here we are going to go to Stat, Basic Statistics, and select Normality Test. We are going to select the column variable diameter, is where our data is located, and we can put some title here and always select as a default the Anderson-Darling test. Click on OK and we have our normal distribution analysis. And remember, if it's over or above 0.05, we have a normal process. This is a beautiful process. Let's run the analysis. Really is I love Minitab because it's very easy to do this analysis. So let's go for Stat, Quality Tools, and we are going to select the Capability Analysis Normal. In the Capability Analysis Normal, what we are going to select now is going to pop up this window of menus. We are going to select the column diameter. In the subgroup size, it's important to mention that subgroup size is related to the sample size that you are taking. So in this case, we have just these 25 samples, but let's say that I'm going to collect 3 samples every hour. So I take the 3 samples, next time I take another 3 samples, and I do every hour 3 sample size. Okay, so I hit OK, and I have my beautiful CPK, where I can observe that I have here my CP value that is excellent, 1.71. My piston ring is quite critical, right, in an engine. So I need in this 1.67 or above, so I'm okay. So right now we verify that the process is stable, that we have the normal distribution, we run the analysis, and we need to report out the conclusion that is pretty good. Okay, so remember, we reviewed the idea, the requirements, the formulas, and we have a practice. So we learned today that the comparison between variability and the spec is a life or death challenge. Understanding capability analysis, we are going to have a powerful tool that is going to help us to know how much the variability is affecting the spec, and also is going to help us to compare when we do an improvement, and also to drive our products to the excellent. Thank you very much, and continue with us seeing more videos. and also is going to help us and also to drive our products to the excellence. Thank you very much, and continue with us seeing more videos. Also, it's very important to use the tools and send us any comment that you have or question that you have regarding the tools. Most important thing is to use and apply these excellent tools.